For decades, cognitive theories of text comprehension operated on a straightforward assumption. They viewed reading as a linear, continuous effort, where a person starts at the beginning of a text, reads to the end, and builds a complete, homogeneous mental model of the information. In professional and academic settings, the process looks different. A researcher or an engineer often scans a dense report specifically to locate a single data point or a relevant clause, bypassing the majority of the document once that objective is met. Consider this physics textbook. When a student opens a volume of this scale, they are usually looking for a specific piece of evidence rather than attempting to absorb the entire book in one sitting. We can analyze this behavior using a short excerpt detailing early atomic models. We will treat this specific paragraph as our baseline dataset. Suppose we pose 3 different questions to a student using this text. First, in what year did Rutherford conduct his experiment? Second, what type of particles did he use? And third, how did Rutherford's atomic model differ from Thomson's? Each of these questions triggers a nonlinear cognitive pathway. The student is no longer reading for global comprehension. They are executing a goal-oriented search. This is the mechanism of document search. It is the consulting of a source using specific executive control processes to locate task-relevant information. If a student takes an exam with closed books, these same executive control processes have to pull exclusively from internal long-term memory. We often assume that an open book environment simplifies the task. However, from a cognitive standpoint, extracting an answer from an external document is a distinct challenge that can be more taxing than simple recall. To understand the difficulty, we must map the cognitive pathways of question answering, comparing the automatic propagation of internal memory against the friction of external document navigation. Document search functions as a unique, resource-intensive cognitive activity with its own specific architecture. Let us establish the baseline scenario, a student answering a complex physics question strictly from long-term memory. Gracer and Franklin described this in their Quest model. The first phase involves parsing the question's core focus. For a query about Rutherford's atomic discoveries, the brain activates specific knowledge nodes for Rutherford and atoms. This initiates an automatic arc search procedure along causal pathways. Logical and pragmatic rules naturally constrain this internal search space. These rules limit the amount of irrelevant data the brain must process to reach the answer. Because it relies on the automatic, cascading propagation of pre-existing data networks, memory-based retrieval functions as a highly optimized biological process. Now, consider the significant shift when that same user must instead extract the answer from an external document. The cognitive burden changes immediately. The searcher now manages 2 distinct information sources at once, the question in working memory and the external text's physical topology. Because this conceptual network is external, automatic activation cannot propagate through the searcher's mind. The searcher must evaluate the external knowledge base manually. They scan for structural signaling devices, like headings, indexes, and tables of contents, to find a path to the answer.
This forces the user into deliberate reasoning. They must constantly check the external text cues they find against the internal question focus held in their memory. An open book scenario shifts the cognitive burden rather than eliminating it. The mental effort moves from retrieval to the management of dual-source information. We can quantify the difficulty of this external search using Peter Mosenthal's framework, which identifies 4 specific dimensions of complexity. Mosenthal's first dimension is document complexity, governed by information volume and structural signaling. Dimension 2 evaluates the query type, as concrete facts are easier to find than abstract relationships. Dimension 3 measures the inferential match distance between the query and text. Finally, Dimension 4 considers the plausibility of distractors, irrelevant data sharing features with the requested information. Without the automatic arc search of memory, these 4 variables dictate the actual effort required to retrieve information from a document. The dimension of distractors shows exactly how environmental noise disrupts the visual search process. Distractors are text elements that share semantic or visual features with the target, creating false positives that confuse the scanner. In our atomic models text, a search for Rutherford's data will inevitably pass over details about Thomson's model. Since both sections use similar scientific vocabulary, Thompson's data can appear relevant during a rapid scan. When the eye encounters a distractor, the search pattern halts. The user must pause and engage their working memory to determine if the information actually satisfies their goal. Skilled document search relies just as much on the ability to discard irrelevant data as it does on the ability to locate a target. The physics questions from our first scene demonstrate how the structure of a query changes the brain's relationship with the text. A shallow query, such as asking what type of particles were used, allows a user to bypass deep semantic processing. They are simply looking for a noun next to a specific keyword. By leveraging these external cues, the user can jump straight to the answer without building a mental model of the entire paragraph. Compare that to an abstract query, such as asking for a comparison between Rutherford and Thompson's models. This comparative task forces the reader to fully reconstruct the propositional networks of both concepts. They must hold both models in working memory to identify the differences, mimicking the state of deep comprehension. Text comprehension exists on a spectrum of depth. The level of semantic processing is a variable determined by the structural demands of the user's objective. Expert document search uses external structural cues to bypass the need for global meaning. Opening a reference document introduces a series of complex interactions, including visual scanning and the constant evaluation of potential distractors. Now, information retrieval is a resource-intensive interaction between executive control, your working memory, and the document's design. Instructional designers and engineers must build environments that support this nonlinear reality, prioritizing clear structural signaling for the goal-oriented reader. Reading represents a dynamic negotiation with information, governed by the specific requirements of the search.